Have you ever wished you could literally sense the world with superhuman clarity?
Hmm.
Like, not just see something, but understand its every minuscule wiggle and hum. Maybe know the exact frequency of your cat's purr.
Or pinpoint the precise moment an idea sparks in your brain.
Yeah, it's a captivating thought, isn't it? Sort
Definitely.
of strip away the everyday noise and perceive things
Yeah.
differently. See the hidden details.
Absolutely. And that's pretty much what we're doing today on the deep dive. We're plunging into the fascinating and sometimes, let's be honest, comically contrasting world of sensing modalities.
Right. And we're not just talking about your standard cameras and microphones here.
No, no, we mean technologies that let us peek inside the human body or, scan our environment with incredible precision.
Or sometimes just enough precision to get by, which, as you said, is where some of the real fun starts.
Exactly. So, our mission today is to unpack a stack of sources that compare these amazing technologies.
We'll be looking at three key things. How fast they capture data that's temporal resolution. Okay, speed.
How detailed their view is spatial resolution.
Got it. Detail.
And maybe the most telling part, how much they'll lighten your wallet. The cost.
Yes, the cost. Because you very quickly find these surprising trade-offs and sometimes just a delightful irony in picking the right tool.
Hmm.
Think of this as like your guided tour through the sensory marketplace. We'll see everything from the budget-friendly, just the fax ma'am options,
Circle slightly.
all the way up to the ultra-high-res, I need to know the atomic structure of that thought kind of devices.
And we'll explore that big question. Does more expensive really always mean better? Or can you sometimes get, surprisingly deep insights from humble beginnings?
Get to the core of it.
And what's really helpful, I think, from our sources is how they often visualize these things. You typically see them plotted on a 2D chart.
Okay, yeah.
So on the x-axis, you've got temporal resolution, how fast it is, capturing quick changes.
Faster means further to the right on the chart.
Exactly. And then on the y-axis, you have spatial resolution, how precise it is, pinpointing where things are happening.
Higher up means more detail, clearer picture.
Precisely. But here's the kicker, the part I find really neat.
Mm-hmm.
The size of the bubble representing each sensor on this chart. That shows its relative cost.
Oh, interesting. So you get speed, detail, and price, all in one visual.
You got it. It tells a whole story at a glance,
Yeah,
and you immediately see these clusters, these sort of quadrants, as the sources call them.
right. Each telling a different story about trade-offs.
Exactly. So let's start our tour, maybe in the bottom left corner, the Humble Heroes quadrant.
The humble heroes, I like that. Okay, so this is where the entry-level sensors live.
Pretty much. Perfect for when you just need a general idea, not a whole research paper's worth of data.
And crucially, they won't break the bank.
Not at all. Take the basic temperature sensor. The sources rate it like 2 out of 10 for temporal, 2 out of 10 for spatial.
So not fast, not detailed.
Right. But the cost, only the 3 out of 20. It's the ultimate are you hot or not sensor for body temperature. No frills.
It does one job, simply. It's like asking for the meaning of life and getting a maybe.
Chuckles, exactly. Or look at GS-Arita galvanic skin response. That's 2 temporal, only 1 spatial, and 5 for cost.
So slow again, and even less precise spatially. What's it good for then?
It gives you a general sense of stress or emotional arousal, like is someone generally worked up, but it won't tell you how stressed or what emotion.
It's like getting a vibe check through a really fuzzy old radio. You know something's happening.
But the details are lost in the static.
Yeah,
And then there's the standard webcam.
the workhorse.
Totally. Rated 3 temporal, 3 spatial, and a very friendly 4 for cost. Great for video calls, basic UI stuff.
But you're not going to read the titles on the books behind someone or track superfine movements.
Not a chance. It gets the basic job done.
So the ironic takeaway here, maybe, is that sometimes less is more, especially when the budget's tight.
Absolutely. They provide essential insights without needing, a government grant. They do their job quietly and affordably.
Okay, so that's the humble corner. Let's swing across the chart now, way over to the top right. The high rollers of resolution.
Alas, yes, the high rollers. This is where speed and precision are king, and the price tags. Well, they're often eye-watering.
This is for when you need to count every single nerve firing rate.
Pretty much. Or map tiny variations in muscle activity. Let's look at magnetoencephalography, neurosensing.
Okay.
It scores a massive 9 out of 10 for temporal, 8 out of 10 for spatial.
Wow, so super fast and super detailed.
Exactly. But the cost, 20 out of 20, maxed out.
Ouch. So what makes it worth that?
Well, it's considered the gold standard for mapping brain activity non-invasively with high temporal and spatial accuracy. If you need to know exactly where and exactly when a neural event happens, with sampling up to, say, 5 kilohertz.
Like for tracking how the brain processes language second by second?
Mm.
Or finding the precise origin of a seizure?
Precisely those kinds of demanding applications. It justifies the cost when that level of detail is critical for research or clinical diagnosis.
Okay. And what about muscles? You mentioned mapping variations there.
Right, there's intramuscular EMG, that's also high 9 temporal, 8 spatial, and a hefty 17 for cost, used often in clinical diagnosis.
Intramuscular, so right inside the muscle, not just on the surface.
Exactly. It lets clinicians assess individual muscle fibers, individual motor units. Think diagnosing neuromuscular diseases where you need to detect very subtle problems. Sampling can go up to 10 kilohertz.
So it's like listening to a single violin in an orchestra versus the whole ensemble.
That's a great analogy. You get that fine-grained detail you just can't get from the surface.
But here comes the irony again, right? Let's talk fMRI, functional magnetic resonance imaging.
Yes, fMRI. A classic case study in trade-offs.
Okay, so spatially, it's amazing, right? 1 out of 10. You can pinpoint where stuff happens in the brain with incredible accuracy for research.
Absolutely stunning spatial detail.
But temporally, it gets a 1 out of 10. Sampling might be, what, once every second or two, 0.5 to 2 hertz.
Temporally, it's slow, glacial almost compared to neural activity. And the cost, also maxed out at 20 out of 20.
So how do researchers even use that? It's like having this hyper-detailed map of a city, but you only get traffic updates every 5 minutes. By then, the traffic jam might have cleared.
Chuckles. It is a challenge. They often use it to see which brain regions are activated during a sustained task, rather than the exact timing of individual thoughts. It's about the location over a period.
Okay.
And sometimes they combine it with master methods like EEG to try and get the best of both worlds, the where from fMRI and the when from EEG. The cost reflects the huge superconducting magnets, the complex setup. It really is a spare no expense approach to spatial detail.
Even if the when is significantly delayed.
Got it. So this really highlights that navigating this landscape is all about trade-offs.
Constantly getting both high speed and high detail at the same time, technically very difficult and usually incredibly expensive. You often have to choose. Do you need the crystal clear where or the lightning fast when?
Exactly. Let's revisit that fMRI versus EEG comparison. We said fMRI is 9 spatial, 1 temporal, 20 cost, great where, slow when.
Right.
High density EEG, that's maybe 8 temporal, 4 spatial, and 18 cost. So much faster when for things like brain-computer interfaces or tracking rapid responses.
But the where is fuzzier, less precise location.
Precisely. So the choice depends entirely on your question. Are you mapping static brain regions involved in a task or trying to capture a fleeting neural signal in real time?
It's a fundamental dilemma, and you see this everywhere, not just in brain imaging.
Oh, absolutely. Take video cameras. You've got your basic webcam, 3 temporal, 3 spatial, 4 cost, basic tracking. Then you jump to a high-end 4K camera, maybe 5 temporal, 8 spatial, 16 cost. Much better detail for motion capture research.
Okay, slower frame rate, but way more pixels.
Right. But then, if you need speed and decent detail for something like 3D tracking in VRR, you might go for a high-speed video that could be 8 temporal, 7 spatial, but cost goes up again to 18.
So you trade off some spatial resolution compared to the 4K, but gain a lot of speed.
Yeah.
It really shows, from watching your cat kind of vaguely on a webcam to capturing every tiny muscle twitch in its leap in super slow-mo, there's a price for every pixel and every frame per second.
Absolutely. And it puts those average stats in perspective, around 5.9 temporal, 4.0 spatial, 11.2 cost. Most sensors land somewhere in that middle ground, balancing the features and the budget.
Which means the real skill isn't finding the objectively best sensor.
No, not at all.
It's finding the most suitable one for your specific needs, aligning the speed, the precision, the cost with what you're actually trying to do.
Whether that's building an interface, doing research, or just, exploring what's possible with biosensing.
And these choices play out across all sorts of categories, right? Neuro, cardio, visual, audio.
Muscle. Yeah, it's a diverse field. Look at audio. You've got your standard microphone, maybe 6 temporal, 1 spatial, 4 cost.
Okay. Decent speed for voice, but terrible spatial. It just picks up sound generally.
Pretty much. Can you hear me now? Basic stuff. But then you have ultrasonic microphones. Those jump to 9 temporal, 2 spatial, and 14 cost. Used for high-frequency analysis.
Listening to things we literally can't hear, like bats. or maybe finding tiny flaws in materials through vibration.
Exactly. Because sometimes hearing the dog whistle isn't enough. You need to hear the bat signal or diagnose a machine fault by its ultrasonic signature. It opens up totally different applications.
Fascinating. And cardio. We use ECGs all the time in fitness trackers.
Right, that's the ECG consumer. Probably around 6 temporal, 1 spatial, 6 cost. Great for tracking heart rate during exercise, basic wellness monitoring. Your fitness tracker's best buddy.
Just checking the pulse, making sure you're still ticking.
Exactly. But then there's the ECG, clinical. That steps up to 8 temporal, 2 spatial, and 12 cost.
So faster, a bit better spatially, and double the cost. Why the jump for clinical use?
Because for serious medical diagnosis, every beat really counts. Those subtle changes in the ECG waveform, tiny abnormalities that a consumer device would miss.
Those could be crucial for diagnosing a heart condition early.
Precisely. The clinical version needs that higher fidelity, that extra resolution in both time and signal detail to catch those critical nuances. It's designed for diagnostic precision.
It really paints a picture of this huge spectrum of tools, from the super simple and cheap to the incredibly complex and expensive.
And each one exists for a reason. Each one solves a particular problem, hitting a specific sweet spot on that temporal spatial cost chart.
So wrapping this up, why does this matter to, someone listening? This isn't just a list of specs.
No, it's more like a map for understanding how we gather information about the world electronically, and how those methods range from the beautifully simple to the staggeringly sophisticated.
It's knowing you don't need a Meg machine to take your temperature.
Chuckles. Hopefully not.
But you might need something pretty powerful to truly map a thought process in detail.
And it just highlights the incredible range of tech we have now. Knowing about these trade-offs lets you ask better questions, get more targeted answers, whether you're designing something, doing research, or just curious. You can optimize for speed, or detail, or cost, depending on what actually matters.
So whether you're aiming to build the next big wearable or doing some really groundbreaking research, or maybe you're just deeply curious, hopefully you've now got a better feel for this vast spectrum of sensing.
From that humble temperature sensor just asking hot or not, all the way to the mighty Meg tracing neural pathways, each gives us a unique window.
Defined by its speed, its detail, and that ever-present price tag.
And this deep dive, I think, really shows that being informed isn't about memorizing specs, it's about grasping those fundamental trade-offs.
And appreciating that sometimes the simplest, cheapest tool gives you exactly what you need.
While other times you really do have to pay for those extra pixels or those milliseconds of perception to make the next big discovery.
So here's a final thought to chew on. Given everything we've talked about, temporal resolution, spatial resolution, cost, if you could pick any one of these sensing modalities, and apply it to one specific part of your own daily life, what would you choose? And what fascinating or maybe even deeper ironic insights do you think it might reveal about your world?
Everything we do is available freely on bionichaos.com. Please consider supporting me on Patreon, and don't forget to gently click like, subscribe, and comment.